Hello and welcome to the circuits review. This is a review of a little bit of AC and AC power. So first of all, when we talk about AC circuits, we're talking about circuits to which we have applied a sinusoidal voltage. That voltage is usually written in this way, looking at equation 9.1, where you have a voltage expressed as a magnitude, Vm, a cosine function, and I should point out that in order for phasor analysis and all of the applications and techniques that we use regarding phasors, in order for that to work, the voltage has to be written in terms of a cosine function. So it's cosine omega t plus phi, where omega is the frequency in radians per second and phi is the phase angle. So the phase angle actually displaces the cosine function to the left or to the right, depending on whether it is a positive or negative phase angle. And then the period is basically the time it takes for one full cycle. The period is related to omega, which is also related to F, the frequency in hertz, through equation 9.3. And also the period is 1 over the period is equal to the frequency in hertz. So there are relationships between frequency in radians per second, frequency in hertz, and the period given from expression 9.3. This figure illustrates what happens if the phase angle is changed. So notice if the phase angle is changed from some value phi to 0, the curve shifts to the right. So as the phase angle decreases, or if phi is positive, the sinusoidal function will shift to the left. If phi is negative, the function will shift to the right. So another important characteristic of sinusoidal voltages is the RMS value. And this is also referred to in your textbook as the effective voltage. So you'll see a subscript in your textbook, V effective. By that they mean RMS. This is the formula for the RMS, for finding the RMS voltage of that sinusoidal voltage function that we showed on the previous slide. But RMS is a general calculation which can be found for any periodic function. The only thing that we require is it is periodic. It would have a period t, and we can actually run this integral from any time period as long as we're running it over a total period t. Now, why would you want to do that? Well, you'd want to do that if you had like an interesting function that maybe doesn't have an easy integral at t equals 0, so there may be some other time range where you can take advantage of symmetry on the integration and it's a little more visual. So it doesn't matter the beginning and ending point of your integral as long as the integral is over one period. So the general formula then is whatever that voltage is, we would square it and then integrate it over a period. So that's the square, and that's the mean when we integrate over a period and then divide by the period. And then the root is the process of taking the square root. So root, mean, square, you're actually doing those in reverse order. You're squaring, you're finding the mean, and you're taking the root. In sinusoidal voltages, the RMS voltage is basically the magnitude divided by the square root of 2. But that is not a general formula for RMS. So RMS for different functions can take on different values. The reason that RMS is significant is it's significant in terms of power. So if we have a 100 volt RMS voltage and a resistor in a circuit, that basically would be the equivalent power of a 100 volt DC source and a resistor in the circuit. So it gives us a way of understanding the equivalent DC power that an AC voltage source will deliver. So here's an example just illustrating that you can indeed calculate the RMS value of other waveforms. And this is out of your textbook. I'll leave it to you to go and view the example to understand how the RMS is calculated. using this, but here's the basic formula that's used where this is a current, and we're going to integrate this over a period. We're going to integrate the current squared. So just to step you through how this would be done, we want to first of all identify a full period. So in this example, we might go from minus t over 4 to 3t over 4 so that we've isolated a full period. And that might be the range of our integral t naught to t naught plus t. You could also go from t over 4 to this value out here, which would be 5t over 4, or you could go from any value you choose. But from this illustration, looks like going from minus t over 4 to 3t over 4 might make the most sense. Then you would actually have to break that integral into two portions. One going from minus t over 4 to t over 4, and the other from t over 4 to 3t over 4, because as you note, the function for I would be different. Then you would need to find an equation for this line and plug it into the first integral for I, and an equation for this line and plug it into the second part of the integral for I, and then you could do the procedure. So just to point out then, you can indeed find the RMS value, and if you do that, you will not get I peak over the square root of 2. You get something else, and the reason is this is not sinusoidal. It's a triangular waveform. Now, when we have an AC signal, we can transform that to the phasor domain. And the reason that we want to do that is we want to do that because if we transform to the phasor domain, we get rid of the sinusoidal functions. And so we don't end up with trigonometric transcendental equations that we have to solve, which can be very difficult to solve, if not almost impossible to solve. We end up with exponential functions complicated only by the fact that we will have some complex numbers. So the phasor transform is basically when we have a function in the time domain, we can transform that to the phasor domain by taking the magnitude Vm and then the phase angle phi. And the transform works like this. And as you know, you have probably seen this written as Vm angle phi with the angle symbol. And that's how we typically write phasors in electrical engineering. And this little p here just illustrates that we have taken, this is the terminology for taking the phasor transform. Something that a lot of students don't ever see in Circuits 1 is the phasor diagram. It's kind of an old-fashioned concept, but nevertheless useful, especially when you get to power concepts. So in the phasor diagram, when you have a phasor voltage 10 angle 30, you can illustrate that by a line of length 10 making an angle 30 with the positive horizontal axis. So here are several phasors that are all illustrated in the phasor diagram. So you can see you're illustrating the magnitude and the phase angle in the phasor diagram. So this is sometimes useful for visualizing things like whether things are ahead in phase or lagging in phase, and sometimes useful also for visualizing things like three-phase. So let's talk a little bit about power, because the main point of this lecture is to give you the formulas that are utilized in calculating power in AC. So as a general rule, when we talk about power, we're always talking about power for something specific. Oftentimes we're talking about the power that is delivered to or dissipated in a load. So in this example, we have current coming into the load. We have a voltage across the load. Note that the current and voltage are labeled according to the passive sign convention, which if you get into detailed power calculations, you can determine whether power is being absorbed by or delivered by what's in the black box based on the algebraic sign of the power. And so that's why if you can use the passive sign convention, then you can look at the sign of the power and know if it's being absorbed or delivered. So when we have an AC signal, we have several different terms that we use for power, and the first is instantaneous power. So instantaneous power is basically the power as a function of time. So if we have a voltage that's a function of time, a sinusoidal voltage, and a current that's a sinusoidal voltage, and we take the product of those two, V times I, then we get the instantaneous power. Now, we're going to go through some trigonometric identities because it turns out, first of all, um, you would really like to look, you're not so concerned about the phase of the voltage as you are the difference in phase between the voltage and the current. Why is that? Well, if you think about it, if you have a load that is purely real, it won't change the phase angle between the current and the voltage because there would be no j omega terms in the impedance Z. So the difference in phase voltage in between the voltage and current gives you some information about what's in your load. So because of that, we really want to not just multiply B times I in this form, because phase is, when thinking about power, typically phase is the same to within a constant. So you have some ability in working with AC to define where is t equals 0. So for that case, if we were to call the phase angle on the current 0, then for this problem, the phase angle on the voltage becomes theta V minus theta I. And so then we can take the product of these two and get an expression for power. Now we're going to work on this a little bit by applying a couple of trig identities, but before we do, I just want you to look at the figure here that illustrates instantaneous voltage, instantaneous current, and then the product of those two, which is instantaneous power. And notice a couple of things here. Notice, first of all, the instantaneous power, the frequency is doubled. And also notice that there is a DC offset to the instantaneous power. So both of those things are interesting, and this expression doesn't give us a lot of information about A, what is the DC offset, and B, what is the new frequency. So we'll apply a couple of trig identities here to get an expression for instantaneous power. And once again, before I leave this slide, what is instantaneous power? Its power is a function of time, taken from voltage as a function of time and current as a function of time. All right, so the first trig identity that we'll apply is the cosine alpha, cosine beta identity. And we're going to let alpha be this angle, this omega t plus theta v minus theta I, and we're going to let beta be just omega t. And when you apply that identity, you get to this equation 10.7 right here. So kind of like in the way this first term looks, the second term still has a lot of stuff in it. So we'll apply a second trig identity, cosine alpha plus beta, as shown here in this equation. And so then we'll let alpha be omega t and beta be theta v minus theta I. So we're separating out the phase part from the time domain part. And when we do that, combining everything, we get this three-term expression for the instantaneous power. And you'll notice that this term is a constant, and it appears twice. It appears here, and then it appears here, multiplying the cosine of 2 omega t. And then you'll notice this term is also a constant, the only difference being you have the sine of the phase angle difference instead of the cosine. So we can relate those constants to some defined terms. So rewriting and letting that first constant be p and letting that last constant with the sign be q as defined here, that expression for instantaneous power looks like this, where capital P is defined by this expression, and we call that the average power. Capital Q is defined by this expression, and we call that the reactive power. And so looking at the equation here, we have the instantaneous power is an average power, which is a DC term, so that's our offset for that curve, plus the average power times the cosine of 2 omega t minus the reactive power times the sine of 2 omega t. And the difference between the average power and the reactive power, average power is power that can actually be utilized and delivered to a load. Reactive power is power that's trapped usually in the reactive elements of the load. So if we have some capacitance, our reactive power might illustrate that we basically have a voltage trapped on that capacitive load. If it's an inductor, it might indicate that we have some power in that inductor due to inductor current, but we're not actually able to get it out. It's there as stored magnetic field. So reactive power is because we have stored electric and magnetic fields. Average power is power that we can actually deliver and dissipate in a load. There are some additional expressions or definitions. One is complex power. Complex power is the complex sum of real and reactive power, P plus JQ. The magnitude of that is referred to as the apparent power. So that would just be taking the magnitude of that complex number S. There are units associated with each of these terms. So complex power, the unit is voltamps. Average power, the unit is watts. Reactive power, the unit is voltamp reactive, or VAR. Sometimes the apparent power, reactive power, and average power are illustrated as what's referred to as the power triangle. And so that's illustrated here, where theta is actually theta V minus theta I, the phase angle. And so you can get an idea for the relative magnitudes of P, Q, and S if you have an idea of what the phase angle difference is, theta, or theta V minus theta I. Interestingly enough, if this is power that is delivered to a load Z, and Z is the complex load, you can form a similar triangle for the load impedance. And when I say similar, I mean that in the geometric sense. So the angle will be the same, and the ratios of the sides of the triangle will also be the same. That similar triangle, in place of P, would have R, the resistive component of the impedance. In place of Q, would have X, the reactive part of the impedance, and in place of the magnitude of S would have the magnitude of Z. So if you know the relationship between the real and reactive parts of the impedance in the load, then you don't have to recalculate Q. Once you have P, you can use ratios in order to find Q if you choose. So there are other ways to write complex power. P plus JQ is one. It can also be written in terms of the voltage and current in a load. So I want to point out at this point, this can be anything. So as long as we have a voltage and a current, then the complex power is calculated where voltage is phasor voltage and current is phasor current. It's 1/2 VI star, where star is the complex conjugate of I. If we have V and I in terms of RMS, then it just becomes V effective, I effective star. Now, if the power is delivered to a load, then we can substitute for either V or I in terms of Z and the other parameter. And so this equation becomes I squared effective Z, or V squared effective over Z star. This is only the case when we have power delivered in a load. So if we have a source and we're trying to calculate source power, we're back up to these equations. So there are lots of different equations that can be used in power calculations in AC that are all effectively calculating the same thing. So it's easy to get lost in the equations. At the end of the textbook is a summary that lists all of the different equations and shows what each one is, and really it just depends on the variables that you have at hand in your problem and how it's easiest to make the calculation. But nothing right or wrong with using different methods to calculate P. So if you have a phasor voltage and a phasor current, note here that you can calculate P directly. The only other thing to discuss, I want to go back a couple of slides, and I want to talk just briefly about this angle theta V minus theta I. Theta V minus theta I is defined as the power factor angle, and the cosine of theta V minus theta I is defined as the power factor. And as a general rule, the power factor is going to give us an indication of how much power we can actually get out of the system. So the closer theta V and theta I are together, the closer this is to 0, then the closer I am to having all P and no Q, which means I get most of the power out of my system. So you want, in a system where you're actually trying to pull power out of the system and deliver it to a load, You want theta v and theta I to be close to the same. You want this angle to be close to 0 so that the cosine of this angle is close to 1. So you typically in systems will see power factors of greater than, say, 0.95. So you want P, you want a lot of P and not a whole lot of Q. So this is called the power factor, this cosine of theta v minus theta I. Sine of theta v minus theta I is referred to as the reactive power. So those are some of the key definitions when it comes to power. You should have been exposed to all of this in the Circuits 1 class. I just think it's important to go back over this because later in the semester we will talk about three-phase and three-phase power. It's maybe good to